Hello everybody. In the previous sessions we have seen the definition on convergent sequence. Now let's study problems on convergent sequence. This is Srimati ASHWINI as Assistant Professor of Mathematics. Okay, the first problem is test the convergence of the sequence n plus 1 divided by n. To test the convergence of the sequence, first of all we have to check whether it is a monotonic sequence. So let's write down the given problem as an. So an is equal to n plus 1 divided by n. Next we would be finding what is an plus 1. So to find this, what we would be doing is we would be replacing n by n plus 1 in the given equation, the problem. So I get an plus 1 is equal to n plus 2 divided by n plus 1. Next we have to find the difference of both, that is an plus 1 minus an, that's equal to n plus 2 by n plus 1 minus n plus 1 by n. So let's take LCM. LCM is n into n plus 1. So by cross multiplying you would be getting n into n plus 2 minus of n plus 1 whole square divided by n into n plus 2. Now let's multiply each term and be using a plus b whole square term. On resimplification, I would be getting it as minus 1 divided by n into n plus 1. This is less than 0 for all n belongs to n. So we have got an plus 1 minus an is less than 0 for all n belongs to n, or an plus 1 is less than an. This is nothing but the definition of monotonically decreasing sequence. Now let's consider an. This is equal to n plus 1 by n. When I take a common denominator, I would be getting it as 1 plus 1 by n. You know, n is nothing but a natural number. So whatever value I give for n, you know, an is going to be greater than 1. Therefore, an is bounded below. We know that every monotonically decreasing sequence which is bounded below is convergent. Hence, the given problem is convergent. The next problem is we have to prove that the sequence an given by 1 by n plus 1 plus 1 by n plus 2 plus 1 by n plus 3 and so on plus 1 by 2n is convergent and its limit lies between half and 1. So let's write down the given sequence an as 1 by n plus 1 plus 1 by n plus 2 plus 1 by n plus 3 and so on plus 1 by 2n. And an plus 1 would be the same terms plus 1 by 2n plus 1 plus 1 by 2n plus 2. Next we would be taking the difference of them, which is an plus 1 minus an is equal to 1 by 2n plus 1 plus 1 by 2n plus 2 minus of 1 by n plus 1. You know, this would be greater than or equal to 1 by 2n plus 2 plus 1 by 2n plus 2 minus 1 by n plus 1, which can be written as greater than or equal to 2 divided by 2n plus 2 minus 1 by n plus 1. So I can say an plus 1 minus an is greater than 0, or an plus 1 is greater than an for all n belongs to n. This is nothing but the definition of monotonically increasing sequence. Now let's consider an as 1 by n plus 1 plus 1 by n plus 2 plus 1 by n plus 3 and so on plus 1 by n plus 1. And you know, this is either less than or equal to 1 by n plus 1 n number of times, which can be written as n divided by n plus 1. So next what we do is we have added plus 1 and minus 1 in the numerator, and on simplification I would be getting it as 1 minus 1 by n plus 1, and this definitely is less than 1. Therefore, an is bounded above. We know that every monotonically increasing sequence which is bounded above is convergent. Therefore, the given problem is also convergent. Let's go to the next problem. Prove that the sequence an defined by an is equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial and so on plus 1 by n factorial is convergent and its limit value lies between 2 and 3. This is an important problem. So let's write down an, and an plus 1 would be the same terms of an plus an extra term of 1 divided by n plus 1 whole factorial. Now let's consider an plus 1 minus an. After substituting a an plus 1 and subtracting it from an, when you look into all the terms except 1 by 1 n plus 1 factorial gets cancelled, and you know this is obviously greater than 0 for all n belongs to natural number. So we have proved an plus 1 minus an is greater than 0, or an plus 1 is greater than an for all n belongs to n. Therefore, an is strictly monotonically increasing sequence. Next, I consider an as 1 by 1 plus 1 plus 1 by 2 factorial as 1 by 1 into 2 plus 1 by 3 factorial as 1 by 1 into 2 into 3 and so on plus 1 by 2 into 2 into 3 and so on n. This is nothing but less than 1 plus 1 plus half plus 1 by 2 square and so on plus 1 by 2 raised to n minus 1. Now I'll leave the first term as it is. Then the next terms are nothing but sum of a geometric series wherein a is equal to 1 and r is equal to 1 by 2. So when I use the formula, I would be getting it as 1 plus 1 minus 1 by 2 raised to n divided by 1 minus half. So this is nothing but 1 plus 2 minus of 1 divided by 2n minus 1. So which is nothing but 3 minus of 1 by 2 raised to n minus 1. This is definitely less than 3. We know an is monotonically increasing and bounded above. Therefore, it is convergent to its least upper bound, which is less than or equal to 3. Therefore, limit n tends to infinity an is less than or equal to 3. Excuse me. Now since an is equal to 1 plus 1 by 1 factorial plus 1 by 2 factorial and so on 1 by n factorial, when I add the first two terms, you know the minimum value would either be 2 or greater than 2. So we can write this as an is greater than or equal to 2 for all n belongs to n. See, that is what it says. The equation holds for a1 which is equal to 2. Therefore, limit n tends to infinity, an is greater than or equal to 2. From equations 1 and 2, I can write it as 2 less than or equal to limit n tends to infinity an. This is less than or equal to 3. Now let's solve another problem. Show that the sequence an defined by a1 is equal to root 2 and an plus 1 is equal to root of 2an converges to 2. So let's solve the problem. They've given us that a1 is equal to root 2 and an plus 1 is equal to root of 2an. We shall prove this by mathematical induction. So the steps for mathematical induction is, we first prove that n is equal to 1 and then we assume it for n is equal to m, and then we prove it for n is equal to m plus 1 is true. So starting, I take n is equal to 1. When I put n is equal to 1 in an plus 1 term, I get a2 is equal to root of 2 times a1, and we know a1 is equal to root 2. So we get root of 2 root 2, which is obviously greater than root 2. That's equal to a1. Therefore, we have proved a2 is greater than a1. Now let us assume that n is equal to m is true. That is, am plus 1 is greater than am. Let me multiply 2 on both sides. We would be getting 2 times am plus 1 is greater than 2 times am. Let's take square root on both the sides. So I would be getting root of 2 times a plus 1 is greater than 2 times am. Now let's use the definition of a sequence which is given in the problem. This would become an plus 2 is greater than an plus 1. Therefore, by mathematical induction, we have an plus 1 is greater than an for all n belongs to n. Therefore, our sequence an is monotonically increasing. Now we have to check whether it is bounded above or not. So next what we do is we take a1 is equal to root 2, which is given, and you know this is obviously less than 2. Let us assume that ap is less than 2 for some p belongs to natural number. We multiply 2 on either side, so we get 2ap is less than 2 into 2, that is 2ap is less than 4. Let's take square root on either of the inequality. So root of 2ap is less than root 4, which is equal to 2. And you know root of 2ap according to the definition of the problem would be ap plus 1 is less than 2. By mathematical induction, an is less than 2 for all n belongs to natural number. Therefore, an is bounded above. Hence, an is monotonically increasing and bounded above, and therefore it is convergent. Finally, we have to find the limit values. So limit n tends to infinity, an is equal to L, and limit n tends to infinity, a2n plus 1 is equal to L. Now we know an plus 1 is equal to root of 2an. Let me square on both sides. So when I square on both sides, I get an plus 1 square is equal to 2 times an. Let me take limit on both sides. So limit n tends to infinity, an plus 1 square is equal to limit n tends to infinity 2 times an. We know they are equal to L. So we get L square is equal to 2L, or L square minus 2L is equal to 0. Taking L common, I get L into L minus 2 is equal to 0. So individually L is equal to 0 and L minus 2 is equal to 0. So you know L cannot be equal to 0 since an is greater than 0. Therefore, limit n tends to infinity, an is equal to 2. Hence, the sequence an is convergent and converges to 2. So these are the references which I have used. Thank you my dear students for patiently listening.